Hello everybody and welcome back. On problem 3, we have just two sort of integrals, one indefinite, one definite, and we're just being asked to calculate them. That's okay. What could we do? So, let's see here. In this first one here, we've got, we want the antiderivative of ln of 1 plus x squared. Okay, that's a complicated looking function. What indeed could I do? Well, I could substitute. That certainly crosses my mind because I've got a composition. And what would I substitute? I'd probably let u be x squared plus 1. But then the derivative would be 2x dx, and I don't have a 2x lying around. Okay? I also am I'm a little suspicious of a substitution like this just because this is Calc 2, not Calc 1. But, oh, well, there's this ln here. And maybe I remember from class that ln can be integrated with integration by parts. So I only have so much room. So we'll write this as 1 times ln 1 plus x squared dx. And what am I going to do? I'm going to say, integration by parts, or IBP. And off on the side, I might say something like, let u be ln 1 plus x squared. What would that make du? It'll be 2x over 1 plus x squared. And then we'll have dv is what's left over, so just dx. And that would make vx. So what are we going to have? We're going to have x, so our v, and our u. And we subtract the integral, and then we just switch them around. So now vx times du 2x. I guess technically there should be a dx here. Over 1 plus x squared dx. X ln 1 plus x squared. And now bring those x's together. I'm actually going to bring this 2 out, and I'll get x squared over 1 plus x squared dx. And this looks exactly like the sort of thing we could do what do you call it? Partial fractions. If we wanted to. We don't have to. By all means, we don't have to. And so if you want to, you can be a little clever about it and say x squared, well, that's just 1 plus x squared minus a 1. And then splitting this up, yeah, you have to keep all the functions there with you. But we can split this up into 1 plus x squared over 1 plus x squared, and minus 1 over 1 plus x squared. Dx is in here. But now, of course, this one here is just the integral of 1. And this one here gives me arctan. So I will get x ln 1 plus x squared minus 2. Integral of 1 is x. And then still minus 2, but another minus turns it into a plus 2 arctan of x. And we don't ever forget our plus c. And if we're worried about this, grab a scrap piece of paper and we can derive it again. We should get this answer as well. It's always good to check, especially if you got a little extra time at the end or you're a little worried about your integrals. But there we go. So you'd get the minus 2x plus 2 arctan x plus c from this part, even if you didn't cleverly split things up. Or even from this part. You could have just done it by rational functions. Remember to divide because we've got the same degree on top and bottom, so do your long division first, and you'll be left with 1 and then a minus 1 on top, and you'll be all set. Don't worry about that. Okay, so that's A. Let's talk about B. So this one here is a definite integral, so I should get a numerical answer at the end. And what can I do? Well, again, I'm seeing a multiplication, so I'm thinking integration by parts again. And so, well, I'm a big fan of doing my definite integrals at the end, so the first thing I'm going to do is get an antiderivative. And this means I don't have to carry this 0 and this pi by 4 with me everywhere. I think it saves myself a little bit of writing, and it makes my life a little cleaner and neater. So what can I do? Well, I'm going to, again, do integration by parts. Because we only have so much room, I usually write an IBP just to help the markers recognize what I'm doing. What to do? I'm going to probably let u be sine 2x. du will be 2 cos 2x. And that would leave dv is e to the minus x. V is minus e to the minus x. Why did I do it this way? Well, in general, I find that if you've got e to the something, the derivative of that is basically just going to be e to the something. You haven't really reduced or played around or done anything. And you can make the same argument for the trigonometric functions, but I've seen one of these in practice. So I know that there's a little bit of a trick at the end here. So we can split this up, negative e to the minus x, and sine 2x, that's fine, minus, now we switch things around, so minus e to the minus x, so I'll just change it to a plus e to the minus x, and then 2 cos 2x. I'm also going to bring that 2 out. And there should technically be dx's everywhere. Okay, so the function here is fine. If you want to, you can keep writing it out. Instead, I think I'm going to focus, and I'm going to tell my TA, whoever's marking, I'm telling them that I'm focusing on just the remaining integral. Okay, well, again, multiplication. In fact, it kind of looks like the same question we started off with. So I think integration by parts, because I got two functions that I understand being multiplied together. I'll let u be cos 2x, and that makes du minus 2 sine 2x. Excuse me. And dv will be e to the minus x, and that means v will be minus e to the minus x. And so this becomes minus e to the minus x cos 2x minus e to the minus x. Again, I can pull this minus sign out. And then minus 2 sine 2x dx. And so this will be minus e to the minus x cos 2x. Oh no, it'll be minus, it'll stay minus 2 e to the minus x sine 2x dx. I think I've seen this integral somewhere before. It's the thing I'm being asked to get the antiderivative for. Have I gone in a circle? Not exactly. Not exactly, because if I take this expression here and plug it back in here, we'll find that this function and this function do not cancel one another out. So I haven't gone in a circle. But what we can do is we can say something like, I don't know what this integral is, but I'm going to give it a name. Okay. So then the antiderivative I was asked to calculate, this one up here, turned into minus e to the minus x, this guy right here, sine 2x, plus 2 times, and then minus e to the minus x cos 2x, minus 2, and then my integral again. So we can clean this up a little bit. So we'll get minus 2 here. And then 2 times minus 2, minus 4i. Let's bring the i's all over to the same side. So I'll get 5i is minus e to the minus x sine 2x minus 2 e to the minus x cos 2x. Dividing by 5, I see that the integral that the antiderivatives that I want are going to be minus e to the minus x sine 2x over 5 minus 2 e to the minus x cos 2x. I only have so much space. I'd probably, since I'm running out of space, use some of the blank sheets that we're going to give you at the back of the exam. But there we go. I've got an antiderivative. And now I just plug things in. So 0 to pi by 4. And if you kept the 0 to pi by 4s in throughout the whole thing, I believe some of this will turn into zeros, but this is my preferred method of doing these integrals, and I'm not about to back down now. E to the minus x cos 2x, and again we evaluate from 0 to pi by 4. Alright, so we'll get negative e to the negative pi by 4 sine pi by 2 all over 5 minus negative e to the 0 sine 0 over 5. Well, that guy goes away. Minus 2e to the minus pi by 4 cos pi by 2 over 5. Well, that goes to 0. Minus, again, 2e to the 0 cos 0 all over 5. And so just going all over to the next page, just so ever so slightly, minus e to the minus pi by 4 sine of pi by 2 is 1. This will be over 5. Minus 2, both of these are 1, so minus 2 over 5. I would say minus e to the minus pi by 4 minus 2 all over 5. Okay. So there we go, and that's my answer for this particular question. 6 marks. You can see it took a little longer, and it also sort of had a trick where you had to exploit the fact that derivative of sine is cos, and then the derivative of that brings you back to not sine, but very close to sine. Okay, and we're already on the next page for question number 4. I will do that in the next video.